What's up, pre-calculus students? Mr. Messner coming at you uh, with new stuff. We're going to be dealing with new stuff that you didn't do in Algebra 2. You touched on it a little bit in geometry, but we're going to get into it more here in pre-calculus, and it involves trigonometry. Okay? So what is trigonometry? Well, if you remember from geometry, it's all about understanding shapes, and in particular, the triangle. And the Greeks were made famous for their discoveries of things with right triangles, specific triangles, right triangles specifically. Right triangles are triangles that have 90-degree angles in it. And what's great about a right triangle is if you know one other angle and you know it's a right triangle, you know what the triangle's shaped like because you know all three angles have to add up to 180. So like this plus this, subtracted from 180 gets you the third angle. We'll denote angles using theta notation or anything else, just making sure you understand this is called theta. And it's just typically a variable used for an angle. So what did the Greeks discover about right triangles? Well, the biggest one that you probably know is the Pythagorean theorem. Pythagoras understood that if you had side lengths, that if you square the two legs of your right triangle, that it's equal to the square of the hypotenuse. Cool? We should remember also that with any triangles, opposite the bigger angles or the bigger lengths, the 90-degree angle has to be the biggest angle. The other two have to be smaller than 90 degrees so that we have three angles that add up to 180 degrees. So this longest length we call the hypotenuse. It is opposite the right angle. And then your smaller leg would be opposite the smaller angle, larger leg opposite the larger angle. That's one thing that they know. The other thing that they really exploited was the idea of proportionality. That if you know an angle measurement, okay, let's say this is a very specific angle. Let's not call it a variable. Let's say this is like, 20 degrees or something like that. We're going to be going away from degrees very quickly, but let's start with that. If we know the side lengths of one 20-degree right triangle, we know the proportion, the ratios of any 20-degree right triangle, no matter what the size. So it's like if you know the side lengths of one 20-degree right triangle, you know this ratio of this like smaller leg divided by the hypotenuse would have to be equal to, this probably larger leg, but divided by this larger hypotenuse would have to be proportional. They'll have to have the same ratios. So like this big B divided by C will equal this small b divided by C. This big A divided by C would have to equal this small a divided by C. And this is what the Greeks used to kind of like understand lengths, understand distances, and help them build stuff. They said like, we can scale, we can use models. We can start with a small triangle, understand the lengths of the small triangle, and then boom, blow it up. And things have to be proportional, okay? And they developed these very specific functions that we'll be using for the rest of the year. And to help us remember these functions, we have an acronym called SOHCAHTOA. Okay, and SOHCAHTOA helps us understand that, like, if you got an angle, you have this ratio that's associated with the angle. Now, we're not going to say the angle equals the ratio, but the angle is associated with a ratio. We will say, like, the trig function or this, like, created function, the trig function of the angle is the ratio, okay? And what we are going to remember is the mnemonic SOHCAHTOA, where they said, hey, the whole idea of like the opposite of the angle and the hypotenuse, we're going to use the specific function to talk about this ratio for this angle where we're talking about opposite over hypotenuse, we're going to use sine. So you can see like so, and I'm going to get rid of the Pythagorean theorem. We're not going to use it much. So means like, hey, for the angle, if you want to talk about an opposite to the angle over the hypotenuse, we're going to say like the ratio has to be the sine of the angle. Okay. If you have this angle, right triangle, boom. This is the ratio that's associated with the opposite and the hypotenuse, like the B over the C part. So here, the sine of theta for this one would be over C. But we would find that if we have the same angle, this 20 degrees, that this B over C ratio would equal this larger B over that larger C. Sine of the angle equals the ratio. Now, the next ratio we could talk about is the side length that's like adjacent to the angle. It's very important to understand like where's the angle, where's the hypotenuse, and then relative to the angle, we'll call one of the side lengths opposite and one of the side lengths adjacent. Probably should have like said that a little bit earlier. But like focusing on an angle, okay, if we want to talk about a consistent ratio that must exist for any right triangle with this specific angle, in this case, we'll call it 20 degrees. And you're talking about the adjacent or like this horizontal length divided by the hypotenuse, this A over C, we're going to call it cosine. Cosine, we'll say that if you want this ratio of adjacent over hypotenuse, we're going to have the cosine of the angle. Okay, so in this case, the cosine of this 20 degree or whatever this angle is, the specific angle, is A over C, the adjacent over the hypotenuse. And that would be the same for any triangle with this specific angle. So like little a over C would be equivalent to this big A over this big C because these side lengths have to be proportional because the triangles are proportional. And cosine will deal with that proportionality of adjacent over hypotenuse. Tangent, if you want to look at the ratio of the opposite over the adjacent side lengths, I don't like how I used A in multiple things, but let's change this to opposite over hypotenuse, adjacent over hypotenuse, and this is opposite over adjacent. If you want to deal with this ratio where you're like, hey, I want to like understand what the what the vertical versus the horizontal for scaling purposes. You got this angle. This ratio has to be consistent. We are going to use tangent of that angle to get that ratio of opposite over adjacent. So tangent in this situation would be B over A, but it'd be equivalent to any right triangle with a 20-degree angle, no matter its size. Here, it would be like, for this one, it'd be the same as big B over A. And we'll see once we start using actual triangles and actual side lengths, how things are going to be consistent. Cool. Let's find a couple of ratios. So first we got this angle theta. We see the right angle. We don't know what the angle is. We see that the hypotenuse opposite the right angle. Make sure you label that first. And then I'd call this 3. This horizontal length, this would be like adjacent to this angle versus this side length, which I don't know right now, would be opposite of the angle. Now, to find that missing side length, don't forget the Pythagorean theorem. 3 squared plus, we'll call it opposite squared, equals 5 squared. And hey, guess what? We should remember our Pythagorean triples, or the idea of certain whole numbers make right triangles. So we get that the opposite side length has to be 4. We're not going to call it plus or minus 4 right now, but we actually could. Okay, great. What's the sine of theta, cosine theta, tangent theta? So what we're saying is like, no matter what your triangle is, if it's this angle, whatever this angle is, we're not sure. It can't be anything. It has to be a very specific. I think it's like something like 38 degrees or something like that. It's probably like 650 52 degrees. It's close to 52 degrees around there. I'll show you like how to get that later. You have that specific angle. These are the ratios that must exist, no matter how big we're talking about. So like the ratio of the opposite over the hypotenuse is the sine of our angle. Opposite over hypotenuse. That's the ratio that must exist for any size triangle with that angle. If you're talking about a ratio between the adjacent side and the hypotenuse, the cosine function will dictate that ratio. And here it would be 3/5. Tangent, if you need the ratio of opposite over adjacent when you're scaling or when you're modeling or where you're looking at distances, the ratio for this specific angle, it's not just any angle, it's this very specific angle that produces this right triangle with these side lengths. The ratio has to be this opposite over adjacent. Okay? Cool. Now, what's interesting and not really needed yet, but if sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, and it's not cosine, it's cosine of the angle. The ratio of adjacent over hypotenuse is the cosine of our angle. And the tangent of our angle is opposite over adjacent. Watch what happens if I divide sine and cosine. Well, opposite over hypotenuse divided by adjacent over hypotenuse, we're going to be dividing fractions a lot in this unit. So don't forget that you can multiply by the reciprocal of the bottom. Dividing by 2 is the same as multiplying by a half. Well, opposite over hypotenuse times hypotenuse over adjacent. Don't these cancel and give you opposite over adjacent? And isn't that the same as tangent? It is. So turns out tangent is equivalent to just sine over cosine. Interesting for right now, just like cool fun fact. Sometimes when we're doing modeling, we don't necessarily want the adjacent over the hypotenuse. Maybe it's easier if our calculations were done in a reciprocal fashion. Maybe we want like hypotenuse over adjacent or hypotenuse over opposite. And this is where we have reciprocal functions. These are reciprocal functions. And what we're going to start doing starting now is kind of denote things as horizontal lengths, x lengths, vertical lengths, y lengths, and then hypotenuse almost thought of as like a radius length, like a radius of a circle. So A, B's, and C's are gone. Now we're doing X, Y's, and R's. And we'll stay consistent for the rest of the time, X, Y's, and R's. Remembering SOHCAHTOA, you'd say that the sine of this very specific angle would be the Y over the R. Well, sometimes you don't want Y over R. Sometimes you want R over Y, depending on how you want to do your calculations to do it quickly. And that's where cosecant comes into play. Cosecant would be the reciprocal of sine. We call CSC cosecant. Why is cosecant not the same as the reciprocal of cosine? I don't know. So I can't tell you, but that's what it is. Cosecant. Think about like we're flipping maybe the fraction. We're taking a reciprocal. So we got to flip the letters. Cool? Cosecant, sine's reciprocal. Kind of tricked you on that one. Cosine of the angle, again, is the ratio for the specific angle for all of our right triangles. Adjacent, well, in this case, the adjacent is the x distance over the hypotenuse. Sometimes based on your calculations, you don't want x over r. Sometimes you're going to want r over x, and that's where you're going to use secant. This is secant. Whenever you see SEC, you're not going to call sec. You're going to call it secant. Okay? Whenever you see CSC, you're not going to say cusk. You're going to say that's cosecant. So get used to that. This is the same with like sine, cosine, Why do I call this cosine? It's like, that's just like the abbreviation for it. Secant. So secant is the reciprocal of cosine. Again, why isn't that the reciprocal of sine? I don't know. Maybe think about flipping things, flipping letters. Fortunately, tangent and cotangent kind of makes sense. If tangent is opposite over adjacent, and we're talking about this angle, and this being a vertical distance, a horizontal distance, the ratio for vertical over horizontal will use tangent of the angle. This is the ratio that has to exist for any triangle size. Cotangent would be x over y. Cool. So let's find some reciprocal functions of a right triangle. There's an angle out there. I don't know what it is. I could find it really quickly, but I'll show you how you find it later. The Greeks, they like had some triangles that they knew. And I'll show you like some triangles that like we know the angles and the sides. We could prove it. But then the Greeks, they kind of like measured out a bunch of things and created like tables of ratios for angles. They're like, hey, if you have this angle, these are the ratios you have to have. And they just kind of kept that. And back in the day, in old math classes before calculators, you had to use tables to kind of look up ratios that you were supposed to have. We will not be looking up values, but we will be understanding the ratios and where they come from, how they can be used, and we're going to stick to some very special right triangles, which we'll talk about later. Okay, so that's what like the Greeks did. You know, they said, hey, you want a 25-degree angle? Okay, here's the ratios that you need to use for these lengths if you're going to use a 25-degree angle. Or, hey, if you got this height and this height, that creates a ratio. What's the angle that needs to be created to kind of go up towards that? And you could, of course, expand that to talk about lengths between planets even. So anyways, sorry. This side length ends up being 12. How do I know that? 5 squared plus, we'll call that y squared equals 13 squared. This is 169. This is 25. This is 144. You get that this is plus or minus 12. We're just going to call it positive 12 right now, but we're going to talk about why it could be negative 12 in future lessons. Okay. Sine opposite over hypotenuse for this very specific angle, whatever it is. Its reciprocal cosecant. Flip it. Hypotenuse over opposite. Y over R, R over Y. Cosine, and this is what I would do is like find the regular ones and then flip them to get the reciprocal ones. For this angle, whatever it is, I'm just like we're going to hypothetical, but it's not for any angle. For this very angle, you have the triangle using this angle and it's right. These are the ratios you have to have. It's that easy. Okay. Cool. So just bringing it home. I already wrote it down, but I didn't know we had extra space for this. The reciprocal of sine is reciprocal of cosine is secant. The reciprocal of cosecant is sine. The reciprocal of cotangent is tangent. Again, the reciprocals are flipped. 1 divided by something. 1 times the flip of the something. Now, how do we find angles? Well, again, like back in the day, the Greeks, they just kind of measured, or they had triangles that they knew, which we're going to use mostly. But mathematics started to evolve and started to figure out different ways to find angle measurements. All of a sudden, we were able to program in to computer systems how to find angle measurements without looking up things that were measured in the past. So here's an example. I'm going to show you how we can get the angle using a calculator, but it's actually not important for right now. It's just something we're going to keep in mind for the future. All right, so I got this angle, don't know what it is, but I see that the opposite side is 2. I see that the hypotenuse is 5. Cool. I could find the adjacent side if I wanted to, but let's just stop right there. Well, I know that the opposite over hypotenuse ratio is the sine of the angle. We're going to say the sine of this angle deals with this ratio that we expect. Cool. What if I want to know what theta is? Well, I gotta want to just like get rid of sine. Well, we talked about inverses at the end of unit 5. For example, like we had in the previous unit, log, e's, exponential functions, and we understood that logarithms were inverses of exponential functions. We talked about in lots of math classes that square roots are the inverses of squares. Then we got a little bit theoretical towards the end of unit 5, and we said, like, hey, if f of 2 equals 3, f inverse of 3 has to equal 2. And we talked about like the theoretical inverse function using this notation f with a -1, but really we read it as the inverse of f. This notation is the notation that shows up when we want to undo trig functions. You want to figure out this angle measurement, use an inverse sine. And you say, it's inverse sine of 2/5. Now, back in the day, like, again, they had tables of like, okay, these angles creates these ratios. You could look for the ratio, find the angle, or vice versa. But then mathematicians kind of investigated things further, were able to program in things, and now we can type in to a calculator a inverse sine of 2/5. And we see 23.578 degrees. Now, what's going to be really interesting to show you is like, this could be the same for any of our like ratios, right? Let's kind of figure this out. If this is 5 and this is 2, what's this side length? Well, 2 squared plus, we'll call that x squared equals 5 squared. X squared equals 21. This is root 21. Okay. I could say cosine of theta equals root 21 over 5. Well, inverse cosine of root 21 over 5 is going to be the same as inverse sine of 2 over 5. Because again, these ratios come from the same triangle, the same angle. Inverse cosine of root 21 over 5 is the exact same as the inverse cosine of 2 over 5 because we're talking about the same triangle, okay? It's like if you have this angle in a right triangle, these are the ratios you're going to have, okay? Boom. That's kind of like showing you that. So we can go back and find some of these angles, like that 3, 4, 5. Let's find that specific angle that creates this 3, 4, 5 right triangle. Sine was 4 over 5. Cosine was 3 over 5. Tangent was 4 over 3. Okay, so this is if you have a 53, approximately 53 degree angled right triangle. So this ends up being like 30, 20, 26, something like that. I can't think, 27. Then, if you have that 50-degree angle, these are the ratios you have to have. Oh, okay, that's got to be 4, that's going to be 5. Oh, that's got to be 4, that's got to be 3. Okay, boom. There's the angle that you create. So instead of theta, I could say the sine of 53 degrees. Approximately 53 degrees. And this is like 0.338. Now, again, like this used to be something you looked up in a table, but I'm going to just type in the sine of 53 degrees, and you should see this ratio 0.8. Let's be more specific, 53.130102354. There you go. If you have that 53-degree angle in a right triangle, the ratio of opposite over hypotenuse has to be 0.8. So that means like opposites 0.8, hypotenuse is 1. Opposites 80, hypotenuse is 100. Like the ratio 0.8 has to exist, and you'll have that consistent angle all the time. Sorry for being long-winded, but it's just like really interesting stuff. And sometimes not taught in a way that's really understood. Okay, cool. Here, I have the adjacent side and the hypotenuse. Make sure you label the hypotenuse first to help you with the opposites and the adjacents. Cosine of this angle is 5 over 6. That means the angle has to be equal to the inverse cosine of 5/6. Something that you could look up on a table or now is programmed into calculators. We don't really care. Just understanding the existence of this inverse to help you find the angle if you have the side lengths. Tangent. Inverse tangent of both sides. Something you used to be able to look up on a table, now can plugged in, boom. Doesn't matter what side lengths you use, if you're using the Pythagorean theorem, the ratios will be consistent if you have this specific angle in your triangle. Now, some triangles were just kind of measured and figured out and approximated. Some triangles, the side lengths were known, okay? And they could be proved. And these triangles we are going to call special right triangles. These are the most important triangles for the rest of this semester and for your mathematical lives, these special right triangles. And we're going to start with an isosceles right triangle with an hypotenuse of 1. This is a triangle that you're going to have memorized eventually, or just like known, because we're going to use it so much. Now, if it's an isosceles right triangle and this is 90 degrees, well, 90 degrees plus, double my other angle has to equal 180. Double my other angle has to equal 90. That means my angle has to be 45 degrees. So this angle has to be 45 degrees, and this has to be 45 degrees as well. We're just going to use the base angle. Okay, cool. So that's the first thing we know. It's a 45, 45, 90 right triangle. Okay. Well, what's cool about this triangle is that the legs have to be the same. Opposite angles being the same. Like if this is 45 and this is 45, okay, these side lengths have to be the same. So we're going to call this just like L, and Y we're going to call L. And let's use the Pythagorean theorem to kind of find what this L has to be. Well, since x squared plus y squared has to equal r squared, we're going to say L squared plus L squared has to equal 1, or 2L squared has to equal 1. L squared has to equal a half. Square root both sides. L has to be the square root of 1/2. All right, well, we know that the square root of a fraction is the same as the square root of the top over the square root of the bottom, which is 1 over root 2. We don't like that, square root in the bottom. It's fine. The square root of 1/2 is fine. But back in the day, before calculators, it was not nice to try to take a number like root 2, which is approximately 1.3, but like let's say it keeps going, and try to take that and divide it by 1. And you have to add a bunch of zeros, and it's complicated. What's easier to do is to take like the 1.3 value, whatever it is, and divide that by a whole number. It's a lot easier to work out. So this is why we like to rationalize our answers, which is like get rid of square roots in the bottom. Because back in the day, we didn't used to have calculators. Now, how we do this is by multiplying the top and bottom by the square root in the bottom. Now, why do I do this? Well, root 2 times root 2 is root 2 squared. It's root 4. It's just 2. Boom. This is a lot easier to do by hand. So pre-calculator life, doing things by hand. Oh, it's 1.4. I was off. It was harder to do 1.41421 into 1, try to do that by hand, than it was to do 1.4142 blank divided by 2. Like immediately, you could be like, oh, I know that it has to at least be 0.7. So like 1 divided by root 2. We know at least it's 0.7. So that's kind of the idea. This is why we rationalize. So we have our first special right triangle that we have to know, and this is important, that a 45, 45, 90 degree right triangle with hypotenuse 1 has leg lengths of root 2 over 2 and root 2 over 2. Has to be known, has to be known, has to be known. Okay? But what this kind of brings you to is the understanding of like, hey, if you know any triangle that has a 45 right triangle that has a 45 degree angle, these are the ratios of your side lengths that you have to have. You can take these values and expand them. You can like use the trig function. You can multiply these values by a multiplier. And boom, it's like, yeah, scale things. That's trigonometry. It's essentially just like scaling things, starting with a small thing, blowing it up, or vice versa. So let's say I have a situation like this. It's like, hey, I have a 45, 45, 90, but one of the side lengths is 3. Trigonometry, kind of an understanding proportionality, helps you find the other side lengths. Start with your known 45, 45, 90 triangle with hypotenuse 1 with the side lengths root 2 over 2. Understand that, some multiplier, which can go on either side, things have to be proportional, would create this. And let's do the easiest one first. Let's do this one. Okay. If I have a 45, 45, 90, and I know these are the ratios that have to kind of exist, these side lengths. Well, if this is 5 instead of 1, well, like 1m equals 5, you could just take everything and multiply it by 5. M has 5. So it's like, okay, root 2 over 2 times m. All right, well, that's 5 root 2 over 2. Root 2 over 2 times m. 5 root 2 over 2. Boom. It's like this would have to be the side lengths of a 45, 45, 90 triangle with a hypotenuse 5. Cool. Now, watch this. I'm going to do something really fancy in a second. Not yet. Let's go back to this. Well, like, here's how I like to do it. I say, like, 3 is really root 2 over 2 times some multiplier m. I can solve for m by multiplying by the reciprocal or dividing by root 2 over 2. And I get my multiplier has to be 6 over root 2. Now, I don't like 6 over root 2, so I'm going to rationalize by multiplying the top and bottom by root 2. And I get 6 root 2 over 2, which is 3 root 2. You can divide the top and bottom by 2. Okay, now, isosceles triangle, this has to be 3 since this is 3. The multiplier, the m, has to be 3 root 2. Now, this is kind of what we will see at the end of this lesson. It's like the most important thing. Watch. What's the sine of 45 degrees? Root 2 over 2 divided by 1. Opposite over hypotenuse, that's root 2 over 2. Cool? Well, what's the sine of this 45 degrees? Okay, well, for this 45-degree angle, the opposite is 3, and the hypotenuse is 3 root 2. Well, isn't that 1 over root 2? And isn't that root 2 over 2? Oh, yeah. Oh, yeah. Of course it's going to be root 2 over 2. 45, 45, 90 triangles, no matter what size, proportionalities, ratios will be consistent. Watch. This 45 degree, different oriented with the triangle. Sine. Okay, the opposite is 5, root 2 over 2. The hypotenuse is 5. Well, divide the 5s. You get root 2 over 2? Oh, yeah, of course. Things have to be proportional. You can either go about that understanding like multiplying things to keep the proportionality, or really the trig functions are what we could have used to then find the other side lengths. There's options out there that we'll investigate moving forward. Cool. First special right triangle, 45, 45, 90. Get it in your brains. Get it in your brains. That's better. That. If you have an hypotenuse 1, your side lengths are root 2 over 2. Next special right triangle. We're going to start with an equilateral triangle. Equilateral triangle, the angles have to be the same. So 3 times my angle has to equal 180 degrees. My angle has to be 60 degrees. Okay, cool. So that's 60 degrees. That's 60 degrees. That's 60 degrees. We're going to call all the side lengths 1. Cool. All right. We are going to split this in half. So I'm going to take a line, cut this angle in half, and cut this side length in half, which means this turns into a right triangle. If this is 60 degrees, this has to be 30 degrees. And what we notice is that the side length of 1 got cut in half. Cool. If we have a 30, 60, 90 triangle, hypotenuse 1, the short length has to be a half. Now let's find the long length. Pythagorean theorem is there to help you. My x squared plus my y squared, we'll call this y for right now, equals 1 squared. I'm going to square a half, I get a fourth. I'm going to subtract a fourth from 1. I get 3/4. I'm going to square root. I got the square root of 3 over 4, which is the square root of 3 over 2. And that is this y length. Okay. Here's the next and the last triangle you have to know, but you got to know it down. Here are some things that are going to help you. Again, the hypotenuse is 1, that keeps it easy. The short length is opposite the short angle. 30-degree angle opposite the 30-degree angle is the 1/2 shorter length. Opposite the 60-degree angle is the larger length, root 3 over 2. You have to remember that root 3 over 2 is bigger than 1/2. And it's obvious that root 3 over 2 is bigger than 1/2. Root 3 is bigger than 1. The square root of 1 is 1. The square root of 4 is 2. Root 3 has to be between 1 and 2. Root 3 is bigger than 1. Root 3 over 2 is bigger than 1/2. What we like to call this is the short side, the short leg, and the long leg. Okay? We can orient this a different way. For example, I could all of a sudden throw this on its side like this. And that's okay. This would be the 30-degree angle. This would be the 1/2. This would be the longer side, root 3 over 2, and this would be 1. You need to know this triangle. Okay? Known. But once you know it, then boom, you can kind of blow it up. You understand any triangle with this angle 60 degrees, that's a right triangle. Or any triangle that has the angle 30 degrees and it's a right triangle. You know what the ratios have to be because these triangles have to be proportional. So Let's say you have an hypotenuse of 4. What would be these legs? Let's say you have a short leg of 5. What would be these legs? Let's say you have a long leg of 2. What would be the other legs? We'll start with your known 30, 60, 90, which you need to be able to create. It's got a short side length and a long side length. Well, like you can, understanding either trigonometry and trig functions or just understanding proportionalities, multiply all of these by a multiplier to get different side lengths, bigger or smaller triangles. Well, right here, we can see that 1m equals 4. M, therefore, is 4. This must be 2. This must be root 3 over 2 times 4, which is 2 root 3. What did I do? I just multiplied 1/2 by m, root 3 over 2 by m. What if I have 5? Well, 1/2 m equals 5. M's got to be 10. Okay, so if m's 10, the hypotenuse has to be 10. The long leg has to be root 3 over 2 times 10, which is 5 root 3. There are other ways that you might have learned in geometry to remember this, where it's like based on the small leg, you know the bigger ones, or based on the leg, you know the hypotenuse. I don't like doing it that way, but if you do it that way and you remember that, congrats. Great. Here, the long leg is 2. Well, that means root 3 over 2 times a multiplier gives us 2. I'm going to multiply by 2 and divide by root 3. Giving me 4 over root 3 is my multiplier. I don't like that. I'm going to multiply the top and bottom by root 3. To get 4 root 3 over 3 has to be my multiplier. Okay, so back to this. M is 4 root 3 over 3. That has to be the hypotenuse, 1m. Root 3 over 2m, let's do 1/2 m. So 1/2 m is 4 root 3 over 6, which is 2 root 3 over 3. Now, what is beautiful about this is the consistency of the ratios. The ratios have to be consistent. This is where SOHCAHTOA comes into play. Let's do cosine. Let's do tangent. Let's do cosine. Okay, the cosine of this triangle, that 60-degree angle, the adjacent is the short leg, the hypotenuse is 1, I get 1/2. Cool. Cosine of 60 degrees, that ratio has to be 1/2. This 60-degree angle, the cosine, the ratio for this triangle, 2 divided by 4. It's 1/2. This 60-degree angle, the cosine, 5 divided by 10, 1/2. Yes, things are consistent, proportional, scaled. Greeks. This is the 60-degree angle. Cosine would be this over this. It's going to be 1/2. Okay? So, driving that home. If I ask you, what's the sine of 30 degrees? It's going to be the same for this triangle as it is for this triangle. It has to be. It's the ratio that must always exist for triangles that are 30, 60, 90 triangles. How can we figure this out? Let's break out our special right triangle with a hypotenuse of 1. Oh yeah. Okay, hypotenuse of 1, 30 degrees. We have the long side and the short side. You got to remember this. The short side opposite the short angle, 1/2. The long side opposite the bigger angle, root 3 over 2. You have to know this. It's memorized. Understood. It is a triangle whose angle and side lengths were just known, proved, not calculated or approximated. Known and proved. Sine, opposite over hypotenuse, 1/2. Cosine, adjacent over hypotenuse, root 3 over 2. Thank you, dividing by 1. Dividing by 1 makes it easy. Okay, what if this is a triangle whose long side was 2. All right, well, it's like the long side is 2, then like 2 is equal to root 3 over 2 times m. So m has to be 4 over root 3. I like multiply by the reciprocal. That's like 4 root 3 over 3. So this is like the same that we just did. Oh yeah, we just did it. So this is 4 root 3 over 3. I mean, I've done it. I've done this so many times where it's like, oh, let's create a new example, and then you end up using the exact same things. And that's root 3. Cool. I showed you previously. What's the sign? Okay, well, it's opposite over hypotenuse. 2 root 3 over 3 divided by, which is the same as multiplying by the circle, 3 over 4 root 3. Okay, 3's cancel. 2 over 4 is 1 over 2. Root 3's over root 3's can't. I get a half. I get the same as the sine of this 30 degrees. Of course, it's going to be the same. That's why this idea was invented. These trig functions are going to be invented. What's going to be the cosine? Yep. It's got to be root 3 over 2. 2 divided by 4 root 3 over 3. Same as 2 times 3 over 4 root 3, which is 6 over 4 root 3. 6 over 4 root 3 is the same as 3 over 2 root 3, which is the same as 3 root 3 over 6, which is the same as root 3 over 2. I kind of went quickly through that, but like all it is just simplifying these fractions to get the ratio you expect. Okay. You need to know 45, 45, 90 triangle. You need to know that this is root 2 over 2. I'm going to kind of skip this because we kind of already did it earlier. Sine of this 45 degrees, cosine of this 45 degrees will be the exact same as the sine of this 45 degrees. It has to be, like, because things are consistent. If this is 4, the multiplier is 4. So this is root 2 over 2 times 4, which is 2 root 2. And this is 2 root 2. 2 root 2 divided by 4, boom. Okay, last thing, and you'll see this on your homework, is kind of an intro to inverses and understanding functions and their inverses is what we kind of left off with Unit 5. It's important with trigonometry as well. Let me show you what I mean by that. Let's take this triangle where we got A, we got Y, and we got 5. This is the hypotenuse. I don't know what it is, and I can't find it because I don't have what Y's value is. I got that Y is the opposite. I got the adjacent is 5. Okay, well, I can write at least a kind of understanding of the ratios based on the angle, that the tangent of the angle has to have this ratio. Cool. Now, the question is to write an equation f of a. So what I want is some function where you plug in a and you'll get y. I need to somehow get y by itself. So I'm going to solve for y. How do you solve for y? I multiply by 5. We get that 5 times the tangent of a outputs this y value. Boom, we've just created a function where if you have the angle and you know the base length is 5, you can output the vertical lengths. Okay, so that's the kind of idea of like creating maybe a function starting with trigonometry. What if we want something where we plug in y's and we get a's? Well, let's somehow solve the equation for a so that I have some function solved, some function where if you plug in a y, you'll get a. This is where we have to use the inverse. Again, you don't have to use it right now. You just have to understand how it's used. You're not going to get answers. You're not going to use a calculator. You just got to understand that it exists. Here I got a equals the tan inverse of y over 5. What's so cool about these two equations is that you should understand that they are inverses of each other. If f of a equals y, g of y equals a goes to y goes back to a. These must be inverses of each other. Look at this. If I plug in a, I'm going to get a y. How do you take that y and bring it back to a? Well, like, how do I solve this equation? Set equal to y. I would divide by 5, and then I would tan inverse both sides. Divide by 5, tan inverse. For you guys, it's just important to understand that these ratios, SOHCAHTOA ratios, we can solve for a certain variable. Set up a program, like we talked about before the break. Set up a program something in where plug in an angle, get a length, or plug in a length with another known length, you can get an angle. Outputs based on inputs. Okay? Hope we're picking up what I'm putting down. Do the homework. And hope you watch that intro video if you're my students, because I'll be seeing you guys on Wednesday. Later.